Okay, so hi everybody. I'm going to start talking, but feel free to interrupt me in the middle. And Josh, if I don't see a hand, just barge in and ask a question. We don't even need to raise hands. We are small enough.
And Christian, are you recording?
Okay, yes, great. Looks like we are recording.
Yeah, so I just want to start with the title of the talk, which is Intelligent Maintenance Processes and Systems, and it's intentionally not predictive maintenance or not preventive maintenance. And the point that hopefully I will make soon is that I think that I would like to cover today a broader range of just like what is usually being defined as predictive maintenance or preventive maintenance, and more like think about how data and analytics can help in broadly speaking, optimize processes and systems that are related to maintenance, again, broadly defined, as you will see in a second. Okay, so, oops, that's not good. So what do I want to do today? I want to talk about cover some maintenance-related applications as an emerging area of intelligent operations. I'm going to talk in detail on two examples. One has to do with work I've been doing with BMW that has to do with the car brake problem detection and identification. And the other one will be around more military application around the aircraft maintenance, resource allocation, and scheduling. And then if I have time, I would like to mention ongoing work, part of which Josh is involved in with Amgen and BMW, both have to do with the, again, aspects of maintenance or operating manufacturing lines in the sense that trying to be able to be more systematically and automated in terms of finding the root causes or root cause analysis of quality deviation in manufacturing lines. So, and I want to mention that because strangely enough, in a matter of in a few months, two different companies from two different industries came up with the same need. So that suggests that maybe there is something more broadly going on here. And the second thing is that, again, it may be deviating from the usual notion of predictive maintenance when we actually think about predictive maintenance. So I just wanted to broaden the kind of scope of what we mean by that. So let me just go very quickly about some applications that I think are kind of trying to capture major opportunities when you think about the maintenance-related processes and systems. I think that one trade-off that emerges that data can inform is really the timing of maintenance, right? Where basically what you usually trade off there is how much downtime, how much planned downtime versus unplanned downtime you want to have versus the replacement and maintenance cost. So the trade-off is if I wait too long, I might have a breakage in the line that I didn't plan for, and I will have a much more major downtime. And if I'm doing it too frequently, I'm going to create disruptions in the line anyhow, and also pay more cost, right? So that's kind of one issue. Another issue that emerges definitely when you talk about the maintenance of aircrafts, but not only aircraft, is that often the maintenance have different modalities that essentially are not necessarily coordinated among themselves. And essentially what you're trying to do is to optimize the scheduling of all of these modalities of maintenance so that, again, you're trying to maximize the time or minimize the downtime or maximize the time that the line is actually working or the machine is working. So for example, in aircraft, you might have maintenance for the electronics of the plane and maintenance for the body of the plane and so forth, right? But again, that's just one example. I think that there are more. Another body of applications or domain of applications is what we call early detection. So it's somewhat related to the first topic, but maybe a point by itself, which is essentially something that has to do with, can we understand fast that what we expect from the machine or the line is not what is happening. So what is happening is deviating from what we expected to the extent that we actually want to stop or do something or intervene. And that definitely can be part of the first topic, but not necessarily. It could be also other things, and that has to do with detection, anomaly detection, and finally, or one other thing is diagnostic of deviation. So, in many cases, especially in regulated environment, when you have a problem on the line, it takes time. It's not only taking time to actually find out what is wrong. That can happen in any complex system, not necessarily regulated, but sometimes you actually have to adhere by certain process to actually show that you investigated the deviation in an appropriate way. And that takes time. It takes human capital, and it also takes time in which often the line cannot work, right? So being able to do that quickly is actually something very desirable. And again, analytics can play a role there. And finally, maybe a classical problem that often you have multiple assets that you actually maintain, and you have scarce resources. And now the question is which assets to maintain, in what order, so that you actually get the best performance across multiple assets. Okay, so maybe here, unlike the 4 first bullets, which are mostly something that you maybe can think about it as at the single asset level for the right definition of asset here, but the last bullet is really prioritizing across assets. Okay, so hopefully that maybe explains why I'm really looking at it not as predictive maintenance, but rather as intelligent maintenance, because it has much more than just predictive maintenance. It has elements of predictive maintenance, but it's definitely something broader than that. And I think that there is a good reason why it's an emerging domain of applications, because these systems are, many of these systems are very typically, or they produce a lot of revenue, so that every time that you don't produce, you're actually losing a lot of money, right? So the first example I'm going to talk about is work I've been doing with 2 Master of Business Analytics students here at MIT with BMW. It has to do with car brake problem detection. And the way I'm going to talk about this is I will first talk briefly about the business impact, and then I'm going to describe at the high level, at least, a methodological approach. And I want to highlight there that there will be 3 major issues there. The first one is data augmentation. And I think that's sort of a common problem in many settings in which you want to implement something new, and the acquisition of data to train a model is actually pretty problematic. It's a challenge. So to some extent, what we're going to see today is some sort of a bootstrapping, but when you actually have to do the bootstrapping in some physical world rather than just like generating more samples, right? And then we're going to talk about noise classification. So the idea would be, I hear different noises on the from the brake. I want to be able to associate them with typical problems that can emerge. And then finally, we're going to talk very quickly about, okay, how can I automate a process like that when I want to implement that the noise detection or the part in the recording that is really relevant to the noise will be detected automatically. And again, that's another part of being able to actually use this at scale. So again, what is the issue here? If you think about the brakes is one of the most critical safety element in a car components. And basically, in our case, we're talking about some unusual sounds or noises from the brake system that can be based on the noise can be classified to different types of error or problems that require different types of solutions. And the current state of affairs is that humans, whenever you have a sound like that, humans have to listen to the sound, and they actually do the classification manually. And these are pretty highly trained individuals. So it's actually not only cost money, it also creates bottlenecks because there are relatively limited resources to that. And why this is important? Well, this is important throughout the entire life cycle of the car, starting with the development and testing of the car. Cars are being tested quite a bit before they go on the road. And basically, whenever whenever you're missing things in this stage, you're going to have to pay down the road a lot of warranty money. And on the other hand, you want to control the amount of manpower that you invest here. And then in the different use cases of how do you actually use cars, whether it's a car sharing a service or customers buying it, you want to improve the customer experience, and you want to be able to be very responsive to tell a customer, hey, you have a problem with that, let's just fix it, or even initiate an alert to the customer that there is a problem with the car. So for all of these reasons, there are multiple use cases that sort of motivated the company to go in that direction. And I just want to sort of go over the high level things that we had here. So we started with 180 samples that were recorded in testing cars, right? That cars that test drivers are driving. This was a special setting that was installed there of microphones near the brakes. But the problem is that and what you see here, these are, the normal no brake noise, and then the 5 conditions that are errors, as you can see here, they are highly imbalanced, right? And if you want to actually create classification, reliable classification of all of them, then you have to do something with this imbalance. But it's not obvious, unlike let's say you just want to generate demand samples or something like that. It's not clear how you do bootstrapping here, right? Because the input, the sample, is an entire recording, right? So the question is, how do you do effectively bootstrapping in this setting, right? And the way that we did that is being able to basically take parts of the, identify the parts of the noise in the recording and mix them in a certain way based on some understanding of what the physical, what will actually create a reliable sample. And we were able to up it up to 3,000 samples that were labeled and retrained and created a more balanced training data. So in order then to actually, again, be able to train the model, you have to remember the recording includes parts that are really not the noise and parts that are the noise, but it's not obvious how you actually separate the two up front. This is even before you actually classify the noise, right? So there is one more step here that you need to sort of worry about. And again, we developed some physical tools to be able to identify the noise and really clean the sample, the incoming sample, the input sample into the model. And then there was a feature extraction, so using some expert inputs here, and essentially we developed 2 different models that basically were used to actually predict and classify the noise. One of them is an STM, which essentially it's a neural network model that looks on time series, and it essentially looks on what we see here, the graph that we see here on the 4th column here from the left. One way to think about the noise as a time series, right? Like you basically every time period, every instance, you have an amplitude and a frequency, right? So if you look at it this way, that LSTM is a natural way to think about it. But at the same time, you can also think about it as a picture. Like there's a graph here. So that's why we also applied the CNN neural network that is also often used to do image processing. So we actually developed each one of these models, and then on top of that, we actually build an ensemble model that actually looks on the combination of the 2 models that I mentioned before, and use their relative advantages to actually get superior outcomes. Okay, so so just a little bit, I mean, a little bit about the results, right? So when we started with the first model, which was an LSTM model, but with no augmented data, we had an accuracy of about 80%. We were able with the CNN model to improve it to 90%. Essentially, the CNN model plus the LSTM plus the ENSEMBLE were able to improve the classification of all the classes with and also reducing the variance when you do out of sample random partitions and test the model out of sample. And this is kind of a summary of the results. As you can see here, the performance is not consistent across all types of noise, but nevertheless they consistently almost across the board either improve or keep the same, statistically speaking, the performance in terms of correctly classifying. And just to, again, make sure that people understand the overall picture, we started with the split data into 3 sets. One was used to train the CNN, one was used to train the LSTM, so they were not trained on the same data. And then basically using the predictors, the predictors, we created an ensemble model that took the 12 predictors. We have 6 classes, if you think about it, 1 normal and then 5 problems. So each one of the models created 6 probabilities for each sample in terms of how what is the probability that it belongs to each one of them. The ensemble model took that and created a logistic regression that gave final predictions. That's kind of how the overall model worked. It's fair to say that the actual company is going now to implement that. But one of the things that was a problem is if you actually think about the production line of implementing something like that, and you will find some recording, you cannot just do manually find what the noise is, right? Remember, in order to actually run the model and get the model, we needed to actually create a more kind of refined and cleaned version of the actual noise. So what we actually did, we actually built using a physical device. We actually developed a way to automate the noise cutout, right? And that actually led to another idea that basically, as we cut the noise, right, for the labeled problem, so we actually looked on another approach to cluster new noise, which is based on the distance between that new noise to the noise that were labeled, and that actually also gave some pretty good accuracy for at least some of the noises, and not to all of them. So this is less balanced, but maybe perform quite well on other things. Okay, so I'm ready to move to the next example, but maybe that's a good time. Again, this is something that I believe was getting now into production within BMW, but I'm happy to answer questions before I move to the next example.
I have a quick question. When you're trying to identify the source of the noise, would you be testing it in a controlled environment like a dealership, or like would it possibly be like when the car is running, you would be trying to identify if these noises are happening in the background? So would you have to worry about like other sounds?
Yes, so that's a great question.
These?
So yeah, so I think that now you're touching like, how do you actually extract the noise? Are you going to put internal mics like they put in the testing cars, or are you going to rely on things that are more crude, right? That are maybe more sensitive to outside noises. Mm-hmm. So that's something that they are going to have to test, and I don't know what the results are. But the training data was very much a more kind of special mics that they put in the car near the brakes. So it was recorded during driving, right? So it was under controlled, under real life environment, right? But not necessarily the way you would record it ultimately in the application. So that's going to be another phase where we will need to see what that extra noise or less high quality recording will do to the performance of the algorithm. So it's a great question. So thanks for, I mean, this is again, all the small but extremely important issues that you have to face when you actually want to move from writing a paper or describing a prototype to actually using it at scale in all the cars that BMW are using, right? So absolutely, so, yes. I think that what they are going to do is to debate whether they want to install special mics or just rely on something cheaper, as long as the performance is still reasonable. So they're going to have to trade off this issue, cost and reliability versus the accuracy of the algorithm.
I think I have a question, Retsef,
sure.
which is a lot of the times especially in time series kind of data, the key question is how much do you do in the frequency domain and how much do you do in the time domain? And I was just curious exactly kind of what I'm not entirely sure what the setup here was. Were you using the frequency domain spectrogram to filter out the noise and then do most of the processing in the time domain on the residuals? I mean, or, after you've filtered, or is it a little of both?
So just to be honest, I'm not familiar to all the exact details of the feature engineering, but I'm happy to kind of go back to revisit what they did. It was very much, though, just to be honest, this was really working with sound experts that sort of prioritize what they think is telling here. That's something that we did feature engineering. It was not like just give the computer to know that out of the blue, especially given the fact that we actually didn't have a lot of samples, right? So, I think that maybe you can learn that if you have a lot of samples, but with the samples that we had, we really had to rely on expert opinions about what matters in the noise. And by the way, that's probably why the performance is not consistent across all the types of noise, because some of them have a very different behavior in terms of the frequency of and the amplitude. Some of them, you just look at it, you say, hey, yeah, I can see that something is wrong. And some others, you look at it and you can easily be confused with another noise or with normal noise, right? So I think that, so I'm not sure I can answer to you exactly what was it, but definitely there was a lot of expert opinion going into the feature engineering, so.
Great, thanks.
Anything else? Okay, so with that, let me go to the next example. This is a work I've been doing with several with my colleague Vivek Faras from MIT Sloan, the faculty, and then and Tom Magnanti, and then both PhD and master students from the ORC. And it has to do with the maintenance of aircrafts from a type F-22. F-22 is what is called low observable plane, which is a plane that has a special coating that makes it invisible to detection of radars. But before I talk about this specific example, I just want to highlight that in the Air Force in particular, maintenance is a very, very big issue. And the reason why it's a very big issue that if you actually look on a life cycle cost of an aircraft program, most of the cost is actually not in the development, which is quite expensive itself. Most of the cost is actually going into maintenance. And anything that you can save on maintenance is going to have impact on both things. One, the cost, but the other one is also the mission capable. How many planes are mission capable? And I'm going to get back to that. What is the definition of mission capable? And as you can see here, the Air Force is very, very hot on trying to understand how they can use data to improve a variety of decisions. And, this data is very, very rich because these aircrafts and many parts of these aircrafts are extremely censored. Like they are censored at the level that sometimes from an engine of a plane, you can get, every couple of milliseconds, like 40, 50, hundreds of parameters from different sensors, right? And it's fair to say that currently a very small fraction of this data is being actively used. The other thing that makes it challenging is that, the cost of error here is pretty high, right? Like if something goes wrong, like it's a serious issue, right? It's not just the line is down, like someone can die. So that's kind of create a particularly stringent set of issues. And the last thing that I would like to highlight that is special about maintenance of Air Force is that often what you have here is the combination of maintenance and supply. Like often the maintenance is involving replacing a part, and these parts are actually quite expensive and scarce. So you have to manage both the supply chain that supports the maintenance as well as the maintenance resources, as well as all the other considerations that we talked about before, maybe in the context of a car. And just to make the point here, this is just like an airplane engine is a very, very complex modular component. Okay. Okay. So back to this particular problem, as I said, these are planes that have special coating, and the quality of this coating is not static. Actually, it changes, and it changes in two directions. As you fly, right, the plane under the pressure of flying, of taking off or landing, is getting some scratches, dings, and other damages to the coating, right? And the quality of the coating is measured through multiple, very complex set of features. We actually relied on something that is a statistics of these features that is called the Signature Assessment System, the SAS score. And basically, without knowing, there is a software package that you record all the damages of the plane and where they are, where they're located, and that calculates for you the SAS score. And the SAS score is essentially below a certain threshold or above a certain threshold, the plane is determined to be not mission capable. It doesn't mean that the plane cannot fly. It's not a safety issue. So like it can fly for training purposes, but it does mean that if you now have a combat mission, this plane will not be qualified as capable to do that mission. And that's kind of the metric that the Air Force cares about a lot. Now, how do you actually improve the SAS score? Is by actually doing maintenance, and there are multiple modalities of maintenance. And it's 1 day, 2 days, 3 days, 4 days, and then 14 days is basically when you essentially clean all the damages. You kind of reset the clock. So basically, the one way to think about it is the more you maintain, you reduce more of the damages, right? And then if you maintain for 14 days, you can think about it as reducing all the damages, right? And here you can sort of see someone maintaining. So that's kind of the problem. And what is the actual problem that you need to solve if you have a fleet of planes, right? So what you want to do is to sustain a high mission capable rate, which means that you want many planes to have with low enough SAS score below a certain threshold, okay? And what you want to do is to decide how to maintain these planes under capacity constraints of the maintenance resources, but also with the idea that you really need to fly, which is the thing that takes the SAS in the wrong direction, and you have flying requirements that you can sort of think about them as the training requirements that you need to fulfill and satisfy. And basically, the decisions that you make every day says which planes to fly to satisfy the requirements, and then which planes to put into maintenance and what modality of maintenance in terms of the time of duration of maintenance. Okay. So that's kind of the overall problem.
Can I ask you a question before you?
Yeah, sure, absolutely.
Do you have like a function that relates the flying hours to change in the SAS score, or do you have to learn this function? Or
yeah, so in a second I will talk about this, but essentially we had a lot of data that looked on. So the flying missions there is some variability there, but it's not like gigantic variability. So at a good proxy level, you can say every time I fly, I have some stochastic decrease or increase, sorry, in the SAS. Right? And the way we model that, we use the real data that we have that says, how the SAS evolved as you flew. So we kind of estimate that distribution. And one other things though that is important to sort of distinguish that we kind of modeled some of the damages are what is called heavy hitters, which means that let's say there's one typical heavy hitter that you get some ding in the tail of the plane. And what is nice about heavy hitter that on one hand, it increases the SAS score by a lot, so it's not good. But on the other hand, you can actually maintain it very quickly and increase it back fast. Versus if you have a lot of damages that are equivalent to the same SAS score increase that are spread all over the plane, probably then you will need to actually maintain that in 14 days. So the way we modeled the evolution of the SAS score was through the stochastic increase every time you fly, plus some distribution about how much how many heavy hitters you have based on the data that we had. The other thing that is important here, when you maintain, there is what is called, not all the time, unless you do the 14 days, you don't usually fix all the damage. So we also looked on the SAS score after maintenance and in each one of the modality, and we kind of estimated what will be the decrease in SAS, again, in a stochastic way. You could probably, if we had the full data, full access to the full data of this software, we probably could have done a better job in model that. But since we didn't have that access, we kind of did something more approximate. But when we showed it actually to experts, they actually felt that it's pretty accurate the way we modeled it.
And is the randomness that's associated with how much the SAS score improves for a given level of maintenance, is that related to like the distribution of these?
Yes, but that's why and that was an approximation of what we did, that we just so that's exactly where you could actually get more accurate.
Right.
But the reason by the way, why the flying time is not that important is that most of the damage is caused by landing and taking off. So essentially every time you flew, most of the damage is like, it doesn't matter how much you fly. Right, so it's basically very marginal, right? Okay,
makes sense.
Okay, so these are the two decisions that we need to make, right? Okay, so one thing that sort of, if you want to sort of formulate this as a stochastic control problem, right? You can easily find yourself in a place where the state space is going to kill you, right? Like why? Because if you think about this, like let's say I have 30 planes. The state space will be the state of each one of these planes. That's an exponentially large state space. And trying to solve, let's say, dynamic program or stochastic control with that state space is going to be like pretty daunting computation, right? And so what we decided to do is to really, and not to mention that it's also not a very interpretable operationally, like it's kind of hard to actually apply in the field, right? The people that make those decisions are not like PhDs, to say the least. So what we thought about is to think about what we call index policies, where essentially they obtain a dimensionality reduction in the following way, that is for every possible state of a single plane, right? They actually give you an index, right? So the number of indices that you have is linear in the state space of one plane, right? Which is, doesn't have the exponential nature to it. And basically, how do you actually make decisions? You look on the index of each one of the corresponding states of each one of the planes, right? And basically, you look on how much capacity do you have, let's say for maintenance, right? Let's say currently we have 2. And if this is the index for maintenance activity, you actually going to take the 2 planes with the highest index and you maintain them, right? Now, this is kind of a simplified version of what the real problem is, because we effectively have many more than one binary. We have much more than one binary decision of maintain or not maintain. We have a basically maintain and how many days, and then you have fly or not fly. So, but if you think about that, you can sort of think about, let's say that I can actually generate an index to each one of these activities and then basically take the highest index myopically to actually implement a policy, right? What is the attractive thing about this policy? It's a very simple policy, right? Like just like, it's very interpretable. You have the index. The caveat is that you need to come up with good way to create index policies. And in order to do that, we actually modeled the problem as a very well-known model in learning. that is called the restless multi-arm bandit model, and I'm going to explain that in a second. So, but as I explained that, I want you sort of to think about bandits as arms. So the multi-arm bandits has you have n bandits, and think about it like we have n planes, and each arm has a state that can evolve in two ways. One, when I make an action, namely I pull the hand of the bandit, and in the most general form of this model, I might have multiple modes of pulling the hand, right? Each type of pull will change stochastically the state of the model, of the arm. And what is special about the restless multi-arm bandit, so the regular multi-arm bandit, if I didn't pull and didn't apply any action on the arm, on the bandit, it stays in the same state. The restless multi-arm bandit is not the case, where it actually changes also stochastically when you don't do any activity. So if you actually think about bandits as arms, basically the resources tell us how many arms we can pull, right? And then we actually define the reward that basically says, well, if the state of the arm or the bandit is less than 100, which is the state correspond to the SAS, right? Then we're going to give you a 1, because that means that the plane is mission capable. If it's above 100, we're going to give you 0.2, which means, hey, you can use it for training, but it's not mission capable. And then 0 if it's in maintenance, because you cannot really use it, right? So what you want to do in the multi-arm bandit is to really think about the steady state kind of a control of these arms, and how do you pull them in order to maximize your reward over infinite horizon, right? And to some extent, that looks like a good proxy of our model. And what is nice about that in this setting, we know both theoretically as well as computationally, and theoretically, this is depending on the exact variant of the model, we know that index policies are either optimal or near optimal. And there are various ways in which you can actually calculate index policies to within the context of multi-arm bandit. And one of them is basically through the following LP relaxation, which is at a high level. What we do here, we are looking on a fluid approximation, an average, long-run average approximation of the average behavior of the system, where the X variables, the decision variables of the linear program, looking on the total expected discounted time you're in action, that action U will be selected for an aircraft at state S, right? And basically the reward is, well, the fraction of the time that I'm in state S times the reward in state S. And what you see here, this is a flow conservation constraint that basically say that on average, the system has to evolve based on the probability of moving from one state to another. This is something that we estimated from exactly the things that Josh asked about before. So we had these estimates of these probabilities. So that's kind of this constraint that makes sure that on average, the system behaves according to the stochastic process that we believe governs the system. And then the second constraint here ensures that on average, we don't use more than the capacity that we need, and that on average, we actually satisfy the flying capacity constraint. So as you can see, this is a relaxation of the problem, right? Because in the real problem, you actually need to satisfy all of these constraints, or the last two in particular, with probability 1. And here we just require that they will be satisfied on average. Okay, so that's not the exact problem. That's an approximate problem. And what we did here, this is a linear program that when you solve it, and actually you need to sort of think carefully how you solve it, because if you actually think about this, if you have quite a lot of states, that could be a pretty large LP, but nevertheless, we can actually solve very large LPs quite fast. So what we did here, we used something that is called the reduced costs of the linear program, which essentially gives you some sense on the marginal cost of each action, right? And we use that as our the way to create the indices, right? So what you see here, it's a sample of an index policy that basically looks on the x-axis is the SAS, right? And remember that we have, yes, with heavy hitter and without heavy hitter, right? So we have two indices, right? And again, once you create that, then operating the system will be basically just applying myopically, choosing the highest indexed policy, the highest indexed plane for each type of action, okay? So these are the maintenance decision indices. You see that they make sense in terms of the more you actually, the SAS number is higher, you are more likely to actually prioritize a longer period of time of maintenance. So what we did next is to simulate this policy, right? And we did that, and basically we took two types of policies here, right? One that you just make decisions about maintenance, and these are the kind of rules that they currently use, right? Basically, they do heavy hitters first, and then they basically select random. That was what we understood the current policy that they had, right? So they basically say, if I have an opportunity to fix a lot of SAS in a short amount of time, let's just do that. Other than that, they didn't really have any explicit rules, and the flying was random, right? What we tested this against was our policy that really had indices both to the flying as well as to the maintenance beyond just heavy hitter. And we simulated that. So what you can see here are the results of the current policy and the index policy that we created for different number of maintenance bays. So that's as you increase the capacity of the maintenance in both places, you actually, and the entries in the boxes are the mission capable rate that we have. And again, mission capable rate is above, is being below 100 SAS score. So what you see here is that we actually dominate them in almost all scenarios, where clearly when the capacity is relaxed, right, then we don't do as much better than them. If the capacity is constrained, we are doing much better than them. And what the rows here are different assumptions about how much residual is left when you don't do overhaul maintenance, right? So we actually check that, and clearly when it's actually when this is high, so namely the effectively speaking, the capacity of the maintenance is constrained more because you do less in the same amount of time, right? You can see that in both directions, when you reduce the number of bays or assume that you have more residual after maintenance, you actually get more improvement, right? And 7-9% or even more than that improvement is actually pretty high. And I think that in most cases, the number of bay was around 4. So if you actually believe that, then the improvement is dramatic, right? If you look on the column 4 between the two policies, okay? So the takeaway from this is that this is actually could have pretty high benefits. But I also want to mention that you could actually take this index policy and translate that, and I'm not going to go over all the rules, but what was nice about that you could actually translate these index policies to actually a simple set of rules that you could actually communicate to the operator. If you just do that, follow these 4 rules, that basically will be implicitly implementing the index policy, effectively speaking. So the other thing that was very important here, the insight that was important here, is that flying decisions are actually equally important when you want to actually optimize the system. And that's very interesting because currently the flying decisions are being made by a different organization than the maintenance, right? So essentially the maintenance are saying, hey, I'm going to take these planes to maintain them, you're gonna deal with the rest, and then the people that fly, they just make random decisions. So they actually also, one of the insights was, hey, you really want to optimize this together. Okay, so maybe before I move to the last topic, time to stop and ask if people have questions or clarification. I'm happy to answer.
I have one quick question. If you go back to where you did the formulation for the optimization, I'm just curious which constraint you're using the reduced cost for. Like, how exactly are you going from reduced cost to the indices?
So each one of the variables has a reduced cost in the optimal solution, right? From the table, from the final table of sequence, right? So that's how we do that.
Okay, I see. Right.
Yeah, you don't see it on this slide, right? I mean, I should have put this another slide to explain that. So sorry about that, but you just look on the final table.
Yeah. Okay.
Other questions? So this was again applied to real data that seems to work. We actually gave it to some officers in the military, and I think it might even have been impacting the way they were thinking about this. Okay.
How did you come up with the 4 sort of rule of thumb guidelines for how to do the maintenance?
This one? This?
Yeah.
Yeah, this was interpreting our index policy. This was specifically looking on our index policies and see this basically looking on this picture. So if you actually think about this, so here's the counterintuitive with this. So look at this way. If you are close to 100, right? You have a high value of maintaining you, right? Especially if you have a heavy hitter, right? Because I can. But if you, as you start to be high value here, actually look at it, your index is going down. Why? Because you say, you know what? In order to actually get you back to being mission capable, I need to actually put you in 14 days, right? I cannot recover. So that's actually, in terms of reward versus resources that you take away from other planes, that's actually not very desirable, right? So I'm actually not going to prioritize you for maintenance, and I'm going to continue to fly you for some training until, you know. So basically, it really prioritizes things around the you know, if you're far away, if you're good, low SAS, you are not prioritized. But also very high SAS, you are not prioritized. So it really takes the planes that are around the cutoff, and it always tries to make them just below, you know, push them below with the relatively short maintenance, right?
What about the big dip around 175?
So I think that has to do again with how much you can get from so I think that here, so as you go below, but this is the heavy hitter, and the size of the heavy hitter is about, I think, 25. So once you get from 25 above 25, it's not enough just to fix the heavy hitter. You again need more maintenance days. So it now makes it less attractive to maintain you. Does this make sense? So think about it like, if I have a heavy hitter, in one day I can bring you down by a lot.
Mm-hmm.
So if the heavy hitter is on average 25, right? Then basically 25 points of SAS, right? So think about it. Once I get beyond 175 or maybe it was 75. I don't remember now the number, but it was something that beyond certain point, even fixing the heavy hitter is not going to put you into mission capable status. So I'm now going to wait until I'm not going to prioritize you, because you're going to consume now more resources of maintenance. Does it make sense?
So that makes sense, like why it would keep decreasing, but then why would it spike back up?
Yeah, because now you are attractive for 14 days, right? So
okay. I see.
So now it's justifying, right?
I see. That makes sense.
So it's actually interesting that the optimal policy is doing some smart, non-trivial things but once you understand them, it's actually quite intuitive, right? Okay. Any other questions? So I'm going to talk very quickly about ongoing projects. So I don't have a lot of results there, but I want to actually at least pose the problem, because as I said, I'm going to talk about the engine case, but actually almost an identical problem emerged from BMW, right? And what is interesting is that both of those lines are in products that are highly regulated, right? That like deviations have to do with compliance, warranties, regulatory issues, right? So you really want to fix fundamentally problems in the line very quickly. And what I want to start with is basically with the process, the current process of that we're dealing with that starts with someone observes some outcome that is not good, or either a process outcome, process control outcome, or a final product outcomes, and they basically report the deviation. That's what you see here. There is actually a special electronic form that actually includes free text parts, like both a short description and a long description, but also some more structured classification that has to do mostly with the part and the high-level suspected cause, right? Then once this is filled, right, there's some determination if this is a major or minor deviation, right? And then in most cases, this is going now to a deviation investigator that follow the following process. It starts by actually putting in place hypotheses about what could cause the problem. And each one of them is, again, has both structured part that classify it as well as unstructured description. And then there is an action to sort of see which one of these root causes are valid or not. And that's by a lot of, back and forth with expert operators, right? And then finally, for each one of them, there is a confirmed or not confirmed. For all the root causes that were hypothesized, there is a confirm or not confirm and a rationale why that happened. And then there is a summary of what was the identified root cause analysis, and then some description of the actions that were taken. And there is an action part, which is potentially a separate document that describes what was the action, right? And currently, most of this process is highly manual and ad hoc, in the sense that the way they actually talk about this and communicate about this is pretty ad hoc. When I look now on all the root causes, if I just look at them, other than the high-level classification fields that are with finite number of values, basically there are some free text there that it's actually not clear how you actually compare apples to apples. So when you start a new problem, it really depends on the experience of the investigator, of how good they're going to be able to guess what is happening, how much they remember past incidents, and so forth. But as you can imagine, that's not necessarily the case all the time. And that could create both inconsistency, longer time, irrelevant things. So it's both about time and accuracy and consistency. So the idea that we're trying to do is to really use advanced analytics to do two things: to automate, or at least semi-automate, the process by predicting in advance, given a deviation, what are likely to be the root cause that could be relevant here. And then maybe as another benefit that could stand by itself, to create a much more structured taxonomy to even speak about this in the organization. So that potentially can change the reporting scheme going forward, right? So this is the current thing that we do. And what is interesting here is that if you think about that, there is an interesting combination of structured and unstructured data. And the structured aspect of that is in multiple dimensions. One of them is there's some high-level classification of both deviations and root causes, right? And then the outcomes, yes, no, right? But there's also some structure connection that connects root causes to deviations, right? There's some structure there, right? So we know that certain root causes were raised in the context of a given deviation, right? But at the same time, there is a lot of unstructured data there that also exists. And now the question is, how can we use both the structured and the unstructured data to get to where we want, right? So it's likely to be an LLP. We will need to use natural language processing, but fair to say that it's going to be silly to use that without actually using the structured data, right? And currently we have some ideas that we're quite exciting about that are going to basically allow us to use some embedding approaches. So one set of approaches in natural language processing is to embed a corpus of text into a vector space, and then sort of use that to then build features and build predictive models. But you can do that in two ways. You can do that in an unsupervised way that basically just try to optimize some proximity of words to each other in sentences, right? Or you can actually do that in a structured ways that basically it explains the best some relationship, some more structural relationship between the different sentences. So for example, what we know that root causes that were maybe posed on the same incidents are likely not to be similar to each other, right? And maybe root causes that were applied to different deviations on the same part or on something that looks the same might be actually need to be closer to each other. So our idea is to try and run the embedding and then do the clustering in a way, the unsupervised, in a way that will give rise to, that will agree the most with the structural relationships that we know exist between these sentences, right? And we already have some promising results, but yet to be worked out on. And Josh, feel free to add if I'm missing something before I
think there's another piece of this as well that's sort of interesting, that we have these hypotheses for what the causes of a particular deviation are, and within each hypothesis, usually these hypotheses are structured as sort of two different phrases, a cause and an effect phrase. And one thing that everybody who's worked on natural language processing knows is that the pre-processing of the data really, really matters in the quality of the results that you get. And one of the pre-processing, well, one task that we're working on that could be part of the pre-processing and could be part of this embedding that Retsef described is how do you, if we're interested really in this cause part rather than in the effect clause, like how do you weight an incoming corpus of text? How do you weight the piece of it that's related to a cause higher than the piece of it that's related to an effect? So that's sort of an interesting problem that we're working on as well.
Yeah. So just to thanks, Josh. So just to conclude, I think that this is a very exciting area of applications of intelligent operations analytics, and the reason is it actually in many cases means a lot both on the cost and the revenue side. So I think there will be more and more interest in that. I know that the military is very hot on this. I know that the pharmaceutical and biologics are very hot, the car industry. So I think we're going to see more and more interest in that from industry. And there are some exciting issues there in terms of the technical problems, both at the level of how do you actually bring data together and how you acquire data and how the data acquisition, but also very interesting high-dimensional time series, some interesting connection between structured and unstructured data, and of course I talked about the very high potential impact. So I'm quite excited and see myself do more work on this in this domain in the coming years. So with that, thanks for your attention. I'm happy to have, we are a little bit over time, but if people want to stay and ask a few more questions or discuss a few more things, I'm happy to stay.